Hey everyone, welcome to Mysteries of the Universe, the documentary that's going to take you on a mind-bending ride through the cosmos. Right now, as you're watching this, you're sitting on a tiny blue speck hurtling through a universe so vast, so strange, that it makes your head spin just thinking about it. We're talking about a place where galaxies flicker like candles, stars die in spectacular explosions, and vast, eerie voids stretch out in silence. But today, we're not just chasing stars or planets, we're diving into the biggest puzzle of all. Something that makes up 95% of the universe but refuses to show itself. It's called dark matter and dark energy, the invisible forces that rule everything we know. And trust me, by the end of this chapter you're going to be wondering, what if these forces aren't just shaping the universe, but sending us a message we can't yet understand? Chapter 1. The Darkness That Rules Us. Dark Matter and Dark Energy. The invisible universe. 95% of everything is missing. Let's start with a fact that'll make your jaw drop. Everything we can see, stars, planets, galaxies, you, me, your phone, makes up less than 5% of the universe. That's right. According to NASA and the European Space Agency, ESA, about 27% of the universe is dark matter, and a whopping 68% is dark energy. Together they dominate the cosmos. But here's the kicker. We can't see them, touch them, or detect them directly. It's like 95% of the universe is playing hide-and-seek, and we're losing. So what are these things? Imagine you're looking at a galaxy, a massive swirl of stars like our Milky Way. You'd expect it to spin based on the gravity of all the stuff you can see, stars, gas, dust. But when astronomers like Vera Rubin in the 1970s studied galaxies, they noticed something bizarre. Galaxies were spinning way too fast. The visible stuff wasn't enough to hold them together. They should have flown apart like a merry-go-round spinning out of control. But they didn't. Something invisible was providing extra gravity, gluing the galaxy together. That something? Dark matter. Then there's dark energy, which is even weirder. In the 1990s, teams using the Hubble Space Telescope found that the universe isn't just expanding, it's speeding up. Galaxies are flying apart faster and faster like someone's hitting the gas pedal on the cosmos. This mysterious force pushing everything away, that's dark energy. Data from the Planck mission, which mapped the universe's oldest light, confirms it. Dark energy is the dominant force out there, and it's only getting stronger. Why does this matter? Because dark matter and dark energy aren't just abstract ideas, they're running the show. They shape how galaxies form, how stars are born, and even how the universe will end. But we're stuck studying their shadows, like trying to understand a ghost, by watching the things it moves. Let's dig deeper into dark matter first, because it's the glue holding the universe together. Picture a galaxy like the Milky Way, with its spiral arms stretching across 100,000 light-years. It's got billions of stars, clouds of gas, and maybe some black holes. But when scientists at places like Caltech and the University of Cambridge crunched the numbers, they realized all that stuff only accounts for a fraction of the galaxy's mass. There's something else, something invisible, adding extra gravity to keep it all together. Dark matter is like an invisible scaffold. It doesn't emit light, doesn't absorb light, and doesn't interact with normal matter except through gravity. Vera Rubin's work, published in the Astrophysical Journal, showed that stars at the edges of galaxies move just as fast as those closer to the center. Something impossible without extra mass. Her observations, backed by decades of research, suggest dark matter forms a massive halo around galaxies, extending far above and below their visible disks. How much dark matter is out there? Based on data from the Wilkinson Microwave Anisotropy Probe and the Planck mission, it's about 27% of the universe's total mass energy. That's 5 times more than all the normal matter, stars, planets, everything. Scientists think dark matter is made of particles we haven't detected yet, maybe something called WIMPs, weakly interacting massive particles. Experiments like the Large Underground Xenon Detector in South Dakota have tried to catch these particles, but so far, no luck. It's like chasing a ghost that doesn't want to be found. Here's where it gets wild. Dark matter doesn't just hold galaxies together, it's the skeleton of the universe. When the universe was young, just a hot soup of particles after the Big Bang, dark matter clumped together under its own gravity, creating dense pockets. Normal matter, gas, dust, fell into these pockets, forming the first stars and galaxies. Without dark matter, the universe would be a shapeless mess. Studies from the University of Chicago show that dark matter's gravity even bends light from distant galaxies, a phenomenon called gravitational lensing, letting us see its presence indirectly. But here's the spooky part. Dark matter is everywhere, even in our solar system. It's passing through you right now, but you'll never feel it. Some scientists, like those at the University of Michigan, wonder if dark matter could subtly affect things like planetary orbits or even life over billions of years. Could it have played a role in how Earth formed? Now, if dark matter is the glue holding the universe together, dark energy is the force trying to rip it apart. Let's dive into that next. Okay, let's talk about dark energy, the mysterious force that's making the universe expand faster and faster. Back in 1929, Edwin Hubble discovered that the universe is expanding. Galaxies are moving away from each other like dots on a stretching balloon. For decades, astronomers thought this expansion would slow down over time, pulled back by gravity. But in 1998, two teams, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees, dropped a bombshell. Using supernovae as cosmic rulers, they found that the universe's expansion is accelerating. Something is pushing galaxies apart, and it's getting stronger. That something is dark energy, and it makes up about 68% of the universe, according to the Planck mission's data. Unlike dark matter, which pulls things together with gravity, dark energy acts like an anti-gravity force, stretching space itself. It's not a substance you can scoop up, it's a property of space, maybe tied to the vacuum energy of quantum fields, as theorized by physicists at MIT and Stanford. Einstein's theory of general relativity even hinted at it with his cosmological constant, a fudge factor he added and later regretted to keep the universe static. The craziest part, dark energy is driving the fate of the universe. Right now, it's pushing galaxies so far apart that billions of years from now, we might not see any galaxies beyond our own. The universe could end in a big freeze, where everything spreads out, cools down, and goes dark. Or maybe dark energy will behave differently, leading to a big rip, where even atoms get torn apart. Nobody knows for sure, and that uncertainty is what keeps cosmologists up at night. Here's a mind-bender. Dark energy isn't just out there in deep space, it's everywhere, even in the room you're in, but its effects are only noticeable on cosmic scales. Data from the Dark Energy Survey, which uses a massive telescope in Chile, shows that dark energy's influence has grown over time, overtaking gravity's pull about 5 billion years ago. That's when the universe hit the gas pedal, and it hasn't slowed down since. So why does this matter to us? Because dark energy isn't just shaping the universe's future, it's a clue to its deepest secrets. Some physicists, like those at the University of Oxford, wonder if dark energy could be tied to new physics, maybe extra dimensions or undiscovered particles. Others think it's a sign we don't fully understand gravity. And here's a wild idea. What if dark energy isn't just a force, but something more, like a signal or a pattern we haven't decoded? Let's take a step back. Dark matter and dark energy together make up 95% of the universe, but we're stuck studying them through their effects, not directly. Dark matter holds galaxies together, bending light and shaping the cosmic web. Dark energy pushes everything apart, speeding up the universe's expansion. They're like two invisible giants, one pulling, one pushing, and we're caught in the middle trying to make sense of it all. Scientists have been chasing answers for decades. The Planck Satellite mapped the cosmic microwave background, the leftover glow from the Big Bang, showing how dark matter and dark energy shaped the early universe. Experiments like the Large Hadron Collider at CERN are hunting for dark matter particles, while the upcoming Euclid mission from ESA will map galaxies to study dark energy's effects. But so far, we've got more questions than answers. Here's a quote from cosmologist Katie Freese at the University of Texas, simplified for us. Dark matter and dark energy are like watching a ghost shape the world, without ever seeing the ghost. That's the heart of this mystery. We see their footprints, galaxies holding together, the universe speeding up, but we don't know what they are. Are they particles? Forces? Something we can't even imagine? And what if they're not just random forces, but part of a bigger cosmic story? Think about this. Dark matter might have helped form the galaxies where stars and planets and life could exist. Dark energy might decide how long the universe lasts. These invisible forces aren't just out there, they're part of our story. But what if they're more than that? What if dark energy, with its relentless push, isn't just a force but a message, a signal from the universe itself, waiting for us to crack the code? So, we've explored the darkness that rules us, dark matter, the invisible glue holding galaxies together, and dark energy, the force tearing the universe apart. We've seen how they shape everything, from the birth of stars to the fate of the cosmos. NASA, ESA, and missions like Planck and Hubble have given us clues, but we're still groping in the dark, piecing together a puzzle with most of the pieces missing. But here's the question that'll stick with you. What if dark energy isn't just a force, but a message? Could it be a sign of something deeper, something we're not ready to understand? Is the universe trying to tell us something through the way it stretches and grows? Or are we just ants in a cosmic storm, too small to see the big picture? This is just the beginning. The universe is full of mysteries, and dark matter and dark energy are only the first step. What's next? Could there be other forces, other dimensions, or even other universes hiding just beyond our reach? Stick around for the next chapter because we're diving deeper into the cosmic unknown, and trust me, it's going to get even wilder. What if dark energy isn't just a force, but a message? Imagine a world so close to its star that it's being torn apart, its atmosphere bleeding away into a fiery abyss. A planet so doomed that every scientific model says it should have vanished long ago, swallowed whole by the blazing monster it orbits. Yet somehow it's still there, defying everything we know about how planets live and die. This is the story of WASP-12b, a bizarre, hot Jupiter that's rewriting the rules of the universe. Located 870 light-years away, this gas giant is locked in a deadly dance with its star, orbiting every 1.1 days, faster than Earth spins on its axis. It's a cosmic anomaly, a world that shouldn't exist, yet it does. And its stubborn survival raises questions that make you wonder if we're missing something fundamental about the cosmos. Let's dive into the mystery of WASP-12b, and try to figure out why this planet is still hanging on. To set the stage, let's talk about where WASP-12b lives. It's in the constellation Auriga, a region studied by astronomers at the Harvard-Smithsonian Center for Astrophysics. Discovered in 2008 by the Wide-Angle Search for Planets (WASP) project, this planet is a gas giant, roughly 1.9 times the size of Jupiter but with a mass only 1.4 times greater. That makes it puffed up, less dense, and strangely fluffy for its size. What makes WASP-12b truly wild, though, is its orbit. It circles its star, WASP-12, at a distance of just 2.1 million miles, about 1/40th the distance between Earth and the Sun. To put that in perspective, Mercury, our solar system's closest planet to the Sun, orbits at 36 million miles. WASP-12b is practically grazing its star, completing a full orbit in just 26 hours. That's not a typo, its year is shorter than an Earth day. This insane proximity has consequences. WASP-12 is a yellow dwarf star similar to our Sun but hotter and more active. Being so close, WASP-12b is blasted with intense heat and radiation, making it one of the hottest known exoplanets, with surface temperatures soaring to 4,700 degrees Fahrenheit, 2,600 degrees Celsius. Research from the University of Cambridge, using data from the Hubble Space Telescope, shows that this heat inflates the planet's atmosphere, making it swell like a balloon. But that same heat is also ripping the planet apart. The star's gravity is so strong that it's pulling material off WASP-12b, creating a stream of gas that trails behind the planet like a comet's tail. Observations from NASA's Chandra X-Ray Observatory confirm this material is being funneled into a disk around the star, slowly feeding it. Every second, WASP-12b loses billions of tons of its atmosphere, a process astronomers call mass loss. Here's where it gets mind-bending. According to models developed by researchers at the Harvard-Smithsonian Center for Astrophysics, a planet like WASP-12b shouldn't last long in such a hellish environment. The intense stellar radiation and gravitational pull should strip away its atmosphere in just a few million years, a blink in cosmic time. Given that WASP-12 is estimated to be about 2 billion years old, based on spectroscopic data from the European Southern Observatory, WASP-12b should have been reduced to a rocky core or swallowed entirely by its star long ago. Yet, when astronomers point telescopes like the Spitzer Space Telescope at it, there it is. Still orbiting, still massive, still defying every calculation. This planet is a cosmic paradox, a world that refuses to die. So, what's keeping WASP-12b alive? One clue lies in its structure. Unlike Jupiter, which has a dense core surrounded by layers of hydrogen and helium, WASP-12b's low density suggests it might have a less compact core or a more extended atmosphere. Studies from the University of Arizona propose that the planet's puffed-up state could be due to extreme internal heating caused by tidal forces from its tight orbit. These forces stretch and squeeze the planet, generating heat that keeps its atmosphere inflated. This inflation might slow the rate of mass loss, allowing WASP-12b to hold on longer than expected. But even this doesn't fully explain its survival. Models still predict it should have lost more mass by now. Another possibility is that we're catching WASP-12b at a unique moment in its life cycle. Research from the University of Warwick suggests the planet might be in a transitional phase, where it's losing mass rapidly but hasn't yet reached the point of total collapse. Observations from the James Webb Space Telescope, which has studied similar hot Jupiters, show that some planets can maintain extended atmospheres for longer than predicted, possibly due to complex interactions between stellar radiation and planetary magnetic fields. WASP-12b might have a magnetic field that shields parts of its atmosphere, slowing the stripping process. But this is speculative. Magnetic fields are hard to detect on distant exoplanets, and we don't have direct evidence for one on WASP-12b. There's also the star itself. WASP-12 is an active star, with a strong magnetic field and frequent flares as observed by the XMMM Newton telescope. These flares could be interacting with WASP-12b in unexpected ways, perhaps altering the rate at which material is stripped away. A 2019 study from the University of Colorado proposed that stellar activity might create a kind of feedback loop, where the planet's escaping gas influences the star's magnetic field, which in turn affects how much material the planet loses. This complex dance could be stabilizing WASP-12b's orbit, delaying its inevitable doom. But again, the math doesn't quite add up. The planet's survival seems to defy the timelines we've calculated. This mystery isn't just about one planet. It challenges how we think about planetary systems. Hot Jupiters like WASP-12b are already weird. They're gas giants that somehow ended up closer to their stars than Mercury is to our Sun, unlike our own Jupiter, which orbits at a safe distance. Astronomers believe hot Jupiters form farther out and migrate inward due to gravitational interactions with other planets or the star's disk, as suggested by models from the University of California, Berkeley. But WASP-12b's extreme orbit pushes this idea to the limit. How did it get so close without being destroyed? And why is it still there when every simulation says it should be gone? The planet's appearance adds to the intrigue. Observations from the Hubble Space Telescope reveal that WASP-12b is one of the darkest planets ever found, reflecting almost no light. Its atmosphere, rich in carbon-based molecules like methane and carbon monoxide, absorbs nearly all the starlight hitting it, making it blacker than coal. This darkness, studied by researchers at McGill University, is due to the intense heat breaking down molecules into light-absorbing compounds. The planet's atmosphere also contains exotic materials like vaporized metals that give it a strange, almost otherworldly composition. It's not just a gas giant, it's a cauldron of chemistry, pushed to extremes we can barely comprehend. WASP-12b's survival also raises bigger questions about time and fate. Its orbit is decaying, and astronomers estimate it has just a few million years left before it's fully consumed by its star. That's a short lifespan compared to Earth's 4.5 billion-year history, but it's still longer than our models predicted. Could there be some unknown process, perhaps involving the planet's internal dynamics or the star's magnetic field, that's slowing its death spiral? Or are we simply witnessing a planet caught in a fleeting moment like a snapshot of a car crash frozen in time? The fact that we can observe it at all, using telescopes like Spitzer and Webb, feels like a stroke of cosmic luck. This planet also challenges our assumptions about what's possible. Hot Jupiters like WASP-12b were once thought to be rare, but the Kepler mission, which discovered thousands of exoplanets, showed they're surprisingly common. Yet none are quite as extreme as WASP-12b. Its existence suggests that planetary systems can be more resilient, more chaotic, and more diverse than we imagined. Studies from the University of Geneva propose that planets like WASP-12b might form in unstable systems, where gravitational chaos flings gas giants inward, only for them to survive against all odds. This resilience could hint at new physics or chemistry we haven't yet uncovered. If the idea of a planet defying death in a fiery orbit is blowing your mind, hit that subscribe button now. We're only getting started, and the universe is about to get even stranger. Click to join us as we unravel more cosmic mysteries. The more we study WASP-12b, the more it feels like a puzzle with missing pieces. Its atmosphere, darker than night, is unlike anything in our solar system. Its orbit, so close it's being torn apart, defies our timelines. Its survival, against all odds, makes us question our understanding of stars and planets. Could there be other planets like it, caught in similar dances of destruction, waiting to be found? Or is WASP-12b a one-of-a-kind freak of nature, a cosmic accident that somehow persists? As we peer at it through our telescopes, we're left with a chilling thought. What if we're watching a planet trapped in a kind of time loop, endlessly resisting its fate? That's the mystery we'll carry forward as we dive deeper into the universe's strangest secrets. Chapter 3. The Great Silence. The Fermi Paradox. If you've been with us so far, you know we've been diving deep into the wild, mind-bending mysteries of the universe. Today we're tackling one of the biggest head-scratchers of all time, the Fermi Paradox. It's a question that keeps scientists, philosophers, and even late-night stargazers like you and me up at night. Ready? Let's get into it. Picture this. You're standing on a hill, staring up at a sky bursting with stars. You know there are 100 billion galaxies out there, each one packed with billions of stars and trillions of planets. That's a number so big it makes your brain hurt. With all that real estate, you'd think at least one alien civilization would have sent us a postcard by now, a radio signal, a shiny spaceship, heck, even a cosmic hello scribbled in the stars. But here's the thing, we've got nothing. Zilch, nada, just silence. And that silence? It's deafening. This is the Fermi Paradox. It's named after Enrico Fermi, a brilliant physicist who, back in 1950, was having lunch with his buddies at Los Alamos. They were chatting about UFOs. Yep, even scientists love a good alien story. Fermi out of nowhere asked, "Where is everybody?" He wasn't joking, he was pointing out something deeply weird. If the universe is so old and so massive, and if life is even remotely possible elsewhere, why haven't we seen any signs of intelligent aliens? Why is the universe so quiet? Let's break this down. The universe is about 13.8 billion years old. That's a lot of time for life to pop up, evolve, and start building spaceships. Scientists estimate there could be 100 billion galaxies, each with 100 billion stars on average. That's a mind-numbing number of planets. Even if only a tiny fraction of those planets can support life, say 1 in a million, that still leaves billions of potential homes for alien civilizations. And yet, when we point our telescopes and radio dishes at the stars, all we hear is static. What's going on? To understand this, we need to dig into the math and the science. Don't worry, I'll keep it simple. Back in 1961, an astronomer named Frank Drake came up with something called the Drake equation. It's like a cosmic recipe for figuring out how many intelligent, communicating civilizations might be out there. It looks at things like how many stars form each year, how many of those stars have planets, how many of those planets could support life, and how many of those life forms might develop technology. It's not perfect, but it gives us a way to think about the odds. Here's the kicker. Even when scientists plug in super conservative numbers, like assuming only a tiny fraction of planets have life, the equation still spits out thousands, maybe millions of possible civilizations in our galaxy alone. The Milky Way is 100,000 light-years across, so even if these aliens are far away, you'd think at least one would have figured out how to send a signal we could pick up. But we haven't, and that's where the paradox comes in. The numbers say aliens should be out there, so why aren't they knocking? Let's talk about SETI for a second. SETI stands for the Search for Extraterrestrial Intelligence, and it's been our best shot at finding ET since the 1960s. These folks use massive radio telescopes to scan the skies for signals that don't look natural, like a repeating pattern or a burst of energy that screams, "Made by someone smart." They've listened to thousands of stars and galaxies. They've checked weird signals like the famous WOW signal from 1977, which was a 72-second blast of radio waves that never repeated. Cool, right? But here's the thing. None of these signals have panned out. No alien talk show, no cosmic Morse code, just more silence. So, what's the deal? Why is the universe so quiet? Scientists have come up with a bunch of ideas to explain the Fermi Paradox, and let me tell you, some of them are wild. Let's walk through a few of the big ones, and you can decide which sounds craziest or scariest. First up, maybe life is just super rare, like insanely rare. The rare Earth hypothesis says Earth might be a 1 in a trillion fluke. Think about it. To get life, you need a planet in the Goldilocks zone. Not too hot, not too cold, just right for liquid water. You need the right mix of chemicals, a stable star, a magnetic field to block radiation, and a big planet like Jupiter nearby to suck up asteroids so they don't wipe you out. Maybe Earth hit the cosmic jackpot, and most planets are just barren rocks or gas giants. If that's true, we might be alone, or close to it. But here's the thing. With trillions of planets out there, even a 1 in a trillion chance should still produce a bunch of life forms. So, is rarity really the answer? Another idea is that life is common but intelligent life isn't. Maybe bacteria and slime molds are all over the universe, but creatures smart enough to build radios are super rare. Evolving brains like ours took billions of years on Earth, and it wasn't a straight line. Dinosaurs ruled for 150 million years and never invented Wi-Fi. Maybe intelligence is a freak accident, like winning the lottery twice in a row. But even if intelligent life is rare, the sheer number of planets suggests at least a few brainy aliens should be out there. So, why no contact? Here's where things get a bit darker. What if intelligent life is out there, but it doesn't last long? This is called the Great Filter, and it's one of the creepiest ideas in the Fermi Paradox. The Great Filter says there's some hurdle that most civilizations can't get past. Maybe it's early on, like developing complex life, or maybe it's later, like surviving long enough to explore the stars. What if civilizations tend to wipe themselves out? Think about it. Humans have only had technology for a couple hundred years, and we're already dealing with nuclear weapons, climate change, and AI that might outsmart us. What if most civilizations hit a wall, war, environmental collapse, or some tech disaster, and go extinct before they can say hello to the galaxy? The Great Filter is chilling because it makes you wonder, is the filter behind us, or ahead of us? If it's behind us, maybe we're one of the lucky few who made it through, but if it's ahead, well, that's not great news for humanity. What if we're speeding toward our own cosmic dead end? Let's pivot to another idea, one that's a little less depressing but still weird. What if aliens are out there, but they're hiding? This is called the zoo hypothesis. Imagine the galaxy is like a big nature preserve, and we're the animals. Advanced aliens might be watching us, but they've got a strict no-contact policy, like scientists studying chimps in the wild. Maybe they think we're too primitive to handle a meet and greet, or maybe they're waiting for us to hit some milestone, like inventing warp drives or solving world hunger. It's kind of flattering to think we're being studied, but it's also frustrating. If they're out there, why not throw us a bone, a signal, a hint? Why the silent treatment? Here's a twist on that idea. What if they're not just hiding, but ignoring us? The dark forest hypothesis is straight out of a sci-fi thriller. It says the universe is like a dark forest at night, full of hunters. Every civilization is quiet and cautious because broadcasting your location is like shouting in a jungle. You might attract a predator. If aliens are out there, maybe they're staying silent to avoid something dangerous. And if that's true, maybe we should stop sending radio signals into space. Are we being naive, waving our cosmic flashlight around? This brings us to an even spookier thought. What if something is wiping civilizations out? Some scientists, like those at Oxford's Future of Humanity Institute, have suggested the universe might be a dangerous place. Maybe there's a super advanced civilization, or a rogue AI, or a cosmic phenomenon we don't understand, that snuffs out life before it gets too loud. Imagine a galactic lawnmower cutting down any civilization that gets too big. If that's true, the silence isn't just empty, it's a warning. Are we next? Let's take a step back and look at what we're doing to solve this mystery. SETI isn't giving up. They're scanning more stars than ever, using better tech to pick up fainter signals. Projects like Breakthrough Listen, backed by folks like Stephen Hawking and Yuri Milner, are pouring billions into the search. They're even looking for techno-signatures, not just radio waves, but signs of alien tech, like massive solar panels or weird energy patterns. Meanwhile, we're sending our own messages, like the Arecibo message from 1974, a binary hello, beamed toward a star cluster 25,000 light-years away. But here's the catch. Even if someone gets that message, their reply won't reach us for 50,000 years. Talk about patience. We're also exploring our own backyard. Missions to Mars, like NASA's Perseverance rover, are hunting for signs of ancient microbial life. If we find even a fossilized microbe, it'd prove life can exist elsewhere, boosting the odds of aliens. But so far, Mars is quiet too. Europa, one of Jupiter's moons, has a massive ocean under its ice. Saturn's moon Enceladus shoots water plumes into space. These are prime spots for life, and we're planning missions to check them out. But what if we find life there, and it's just bacteria? Does that solve the Fermi Paradox or make it weirder? Let's think about time for a second. The universe is old, but civilizations might not overlap. Maybe aliens existed a billion years ago and their signals faded before we showed up. Or maybe they're out there now, but their signals haven't reached us yet. Light takes a long time to travel. The galaxy is like a big party where everyone shows up at different times. If we're early or late, we miss the action. But with so many stars, you'd think at least one civilization would be around right now, right? Here's another angle. Maybe we're looking in the wrong way. Most of SETI's work assumes aliens use radio waves or light signals, But what if they communicate with neutrinos, gravity waves, or something we haven't even discovered? What if their tech is so advanced it looks like nature to us? Imagine trying to explain Wi-Fi to someone from the 1800s. Maybe we're surrounded by alien chatter, but we don't have the tools to hear it. Are we like ants trying to understand a smartphone? Let's get philosophical for a moment. The Fermi Paradox isn't just about aliens, it's about us. It forces us to ask, what makes us special? Are we a miracle or just one of many? If we're alone, that's kind of beautiful but also heavy. It means we're the only ones telling the universe's story. But if we're not alone, why haven't we found anyone? Oxford's researchers like Nick Bostrom say the paradox might hint at something deeper about existence itself. Maybe the universe has rules we don't understand, or maybe we're part of some bigger experiment. It's enough to make your head spin. So, where does this leave us? We've got a paradox that's equal parts exciting and unsettling. The numbers say aliens should be out there, but the silence says otherwise. Are we alone? Are we being watched? Are we in danger? Or are we just not listening? Every answer raises more questions, and that's what makes the Fermi Paradox so gripping. It's not just a puzzle, it's a mirror, reflecting our hopes, our fears, and our place in the cosmos. As we stare into the great silence, one thought lingers. What if the answer isn't out there, waiting to be found? What if it's buried deep inside us? Some truth about life, intelligence, or existence that we haven't uncovered yet? What if the key to solving the Fermi Paradox isn't in the stars, but in our own minds? Think about that. And stick around for the next chapter, where we'll dive into another cosmic mystery that'll blow your mind. Some stars don't just fade away. They go out with a bang so intense it defies everything we think we know about the universe. When a massive star dies, it doesn't always end in a quiet whimper. Instead, it can transform into something so bizarre, so extreme that it challenges the very laws of physics. We're talking about neutron stars and their even wilder cousins, magnetars, cosmic oddities that pack the mass of the sun into a city-sized sphere and wield forces so powerful they could disrupt life as we know it from thousands of light years away. These aren't your average twinkling lights in the night sky. They're the universe's way of showing off its most extreme creations. So let's dive into the chaos of dying stars and uncover why some refuse to go quietly into the night. Imagine a star, 10 times bigger than our sun, living its life in a blaze of glory. It burns through its fuel in a cosmic blink, just a few million years compared to our sun's 10 billion. When it runs out, it doesn't just dim, it explodes in a supernova, a blast so bright it can outshine an entire galaxy for weeks. Data from NASA's Chandra X-Ray Observatory shows these explosions are the universe's most violent events, hurling elements like iron and oxygen into space, elements that make up the building blocks of planets and even us. But what's left behind after the fireworks? Sometimes it's a neutron star, a core so dense that a single teaspoon of it weighs more than Mount Everest. That's right, imagine scooping up a bit of this star and finding it heavier than the tallest mountain on Earth. How does something so small hold so much power? Let's break it down. When a massive star goes supernova, its outer layers are blasted away, but the core collapses under its own gravity. This isn't a gentle squeeze, it's a catastrophic implosion, crushing atoms so tightly that protons and electrons merge to form neutrons. The result is a neutron star, a sphere just 10 to 20 kilometers across, yet so dense it defies comprehension. Picture squeezing the entire population of Earth into a single grain of sand. That's the kind of density we're dealing with. These stars are so compact that their gravity bends light itself, warping the space around them. According to studies from the European Space Agency, a neutron star's surface gravity is about 1 billion times stronger than Earth's. Drop a pebble on one and it would hit with the force of a nuclear bomb. But density is just the beginning. Neutron stars spin and they spin fast. Some, called pulsars, whip around at 700 rotations per second. Imagine a city-sized object spinning faster than a blender blade. This isn't science fiction, it's real, and we've observed it. The Crab Nebula, a remnant of a supernova seen by Chinese astronomers in 1054, hosts a pulsar that spins 30 times a second, sending out beams of radiation like a cosmic lighthouse. NASA's Chandra has captured X-ray images of these beams, showing how they sweep across space, lighting up gas clouds in their path. Why do they spin so fast? It's all about physics. When the star's core collapses, it's like a figure skater pulling in their arms, speeding up as they shrink. But what happens when that spin combines with other forces? That's where things get even stranger. Enter magnetars, the universe's magnetic monsters. If neutron stars are extreme, magnetars are off the charts. These are neutron stars with magnetic fields 1,000 times stronger than a typical neutron stars, which are already 1,000,000 times stronger than anything we can create on Earth. To put it in perspective, a magnetar's field is so intense it could erase your credit card's data from halfway across the solar system. Scientists at the Max Planck Institute for Astrophysics estimate that a magnetar's magnetic field is 1,000,000,000,000 times stronger than Earth's. That's a number so big it's hard to wrap your head around. If you were within 1,000 kilometers of a magnetar, an impossible scenario since you'd be vaporized, its magnetic field would rip apart the molecules in your body. Even from thousands of light years away, a magnetar's outburst could mess with our planet's electronics, potentially frying satellites or power grids. How do magnetars get this way? It's not entirely clear, but researchers think it starts with the star's collapse. If the dying star was spinning fast enough and had the right conditions, its magnetic field gets amplified during the supernova, like winding up a cosmic dynamo. The result is a magnetar, a star that doesn't just sit there but crackles with energy. They're rare. Only about 30 confirmed magnetars exist in our galaxy according to Chandra's observations. But they're loud. Magnetars can unleash flares of X-rays and gamma rays so powerful they're detected across the universe. In 2004, a magnetar called SGR 1806-20 unleashed a burst so intense it temporarily blinded X-ray telescopes and ionized part of Earth's upper atmosphere, even though it was 50,000 light-years away. What could cause a flare that powerful? Let's talk about starquakes. Yes, stars can have earthquakes. A magnetar's surface is a rigid crust of neutrons, but beneath it lies a chaotic superfluid core. When the magnetic field shifts, it stresses the crust until it cracks, releasing energy in a violent burst. These starquakes can trigger flares that outshine the sun by 1,000,000 times. Scientists at NASA have modeled these events, showing how the magnetic field twists and snaps, like a rubber band stretched too far. But here's the kicker: we don't fully understand what's going on inside a magnetar. The core is a soup of exotic particles, possibly quarks or strange matter, behaving in ways we can't replicate in labs. It's a place where the rules of physics get weird, and we're only scratching the surface. Neutron stars and magnetars aren't just cosmic curiosities, they challenge our understanding of reality. For example, their gravity is so strong it warps time itself thanks to Einstein's theory of relativity. A clock on a neutron star would tick slower than one on Earth. Spend a year there, and you'd come back to find your friends had aged decades. This isn't just theory. NASA's observations of pulsars confirm these effects. Then there's the question of what powers their insane magnetic fields. Some scientists think it's tied to the star's rapid spin, but others argue the field comes from the star's core, where matter behaves like nothing we've ever seen. We're still piecing together the puzzle, and every new observation raises more questions. Let's pause for a moment. If you're learning something new about these cosmic beasts, hit the like button to let me know. And in the comments, tell me, what mystery has blown your mind the most so far? Is it the density of neutron stars, the magnetic chaos of magnetars, or something else entirely? Now let's think bigger. Neutron stars and magnetars are born from death, but they don't always stay dead. Some pulsars seem to glitch, suddenly speeding up their spin for no clear reason. Others, like magnetars, can go quiet for years, then flare up without warning. In 2020, a magnetar in our galaxy woke up after a decade of silence, spitting out radio waves we hadn't expected. Why? We're not sure. Some think it's tied to their magnetic fields rearranging, but others wonder if something deeper, maybe even unknown particles, is at play. These stars are like cosmic time bombs, unpredictable and untamed. And here's where it gets personal. Magnetars, with their insane magnetic fields, could theoretically affect Earth from afar. A strong enough flare could disrupt our technology. Think satellites failing, power grids collapsing, or GPS going haywire. It's rare, but not impossible. In fact, some researchers speculate that a mysterious radio burst detected in 2004 might have been a magnetar's doing. Could a distant star's tantrum really mess with our modern world? We don't know how likely it is, but the possibility is enough to make you wonder. These stars also hold clues to the universe's biggest questions. The elements they scatter in supernovae, gold, silver, uranium, are the seeds of planets and life. Without neutron stars, we might not be here. But their interiors are a mystery. Some theories suggest they could contain strange matter, a state where quarks roam free, unbound by normal rules. If that's true, it could rewrite physics as we know it. Others think neutron stars might be the key to understanding dark matter, the invisible stuff that makes up a quarter of the universe. Every observation brings us closer, but we're far from the full picture. So as we gaze at these cosmic relics, we're left with a nagging thought. These stars, born from destruction, wield powers we can barely comprehend. They spin, they pulse, they flare, and they challenge everything we think we know. But what if one of these distant monsters, say, a magnetar just a few thousand light-years away, decides to throw a cosmic tantrum? Could the death of a star light-years away ripple through space and end life as we know it? The universe is full of surprises, and we're only beginning to understand the rules of this wild, untamed cosmos. Hey, cosmic adventurers, welcome back to Mysteries of the Universe. So far we've wrestled with the invisible grip of dark matter, the universe's runaway expansion driven by dark energy, the eerie voids that defy explanation, and the ghostly whispers of cosmic background radiation. But today we're diving into the heart of darkness, literally. At the center of every massive galaxy, including our own Milky Way, lurks a monster, a supermassive black hole. Ours is called Sagittarius A*, and it's chillingly quiet, for now. Some galaxies, though, show their black holes raging, devouring stars and blasting jets of energy across space. Thanks to groundbreaking data from the Event Horizon Telescope and ESA's Gaia mission, we're starting to unravel these cosmic beasts. But here's the twist. We're orbiting death itself, and we rarely stop to think about it. So let's face the monster at the center and ask a question that'll make your spine tingle. What happens when ours wakes up? Let's kick things off with a wild truth. Every large galaxy has a supermassive black hole sitting at its core, like a king on a throne. These aren't your average black holes, the ones formed when a massive star collapses. Those are small fries, maybe 10 or 20 times the mass of our sun. Supermassive black holes? They're beasts, weighing millions or even billions of times more than the sun. Imagine squashing a billion suns into a space smaller than our solar system. That's the kind of density we're talking about. Our galaxy, the Milky Way, is no exception. At its center, about 26,000 light-years from Earth, lies Sagittarius A*, pronounced A-star. According to NASA and the European Southern Observatory, it's got the mass of about 4.3 million suns, packed into a region roughly the size of Mercury's orbit. That's mind-boggling, right? But here's the thing. Sagittarius A* is pretty chill compared to other supermassive black holes. It's not gobbling up stars or spewing massive jets of radiation. It's like a sleeping giant just sitting there, quietly shaping the galaxy. How do we know these monsters exist? We can't see black holes directly, they trap light after all, but we can see their effects. Astronomers have watched stars and gas clouds whip around galactic centers at insane speeds, pulled by something incredibly massive and invisible. The University of California, Los Angeles, has been tracking stars near Sagittarius A* for decades, and one star, called S2, zips around it every 16 years at speeds up to 3% of the speed of light. That kind of gravitational pull can only come from a supermassive black hole. But it's not just our galaxy. Data from the Hubble Space Telescope and the Chandra X-Ray Observatory show that nearly every large galaxy, spirals, ellipticals, you name it, has one of these beasts at its core. Some, like the one in the galaxy M87, are absolute monsters, clocking in at 6.5 billion solar masses. So, why do galaxies have these black holes, and what are they doing there? Let's dig deeper. Let's zoom in on Sagittarius A*, our galaxy's supermassive black hole. It's named after the constellation Sagittarius, where it hides behind thick clouds of dust and gas at the Milky Way's center. For years, studying it was like trying to see through a fogged-up window. But in 2022, the Event Horizon Telescope, a global network of radio telescopes working together, did the impossible. It captured the first-ever image of Sagittarius A*. It wasn't a photo like you'd take with your phone, but a blurry, donut-shaped glow of superheated gas swirling around the black hole's event horizon, the point of no return. That image was a game-changer. According to the Max Planck Institute for Radio Astronomy, it confirmed that Sagittarius A behaves like a classic black hole, bending space and time in ways predicted by Einstein's theory of general relativity. The glowing ring was caused by gas and dust spiraling inward, heating up to millions of degrees as it gets crushed by gravity. But here's the weird part. Sagittarius A* isn't eating much. Compared to other supermassive black holes, it's on a diet. Every now and then it snacks on a bit of gas or maybe a stray asteroid, but it's not actively devouring stars or lighting up the galaxy. Why is it so quiet? Scientists at the University of Amsterdam think it's because the Milky Way center is relatively calm right now. There aren't many stars or gas clouds close enough for Sagittarius A** to pull in. But quiet doesn't mean harmless. Even in its sleepy state, it's shaping the galaxy. The European Space Agency's Gaia mission, which maps billions of stars, shows that Sagittarius A's gravity anchors the Milky Way's core, influencing the orbits of stars and gas clouds thousands of light-years away. It's like the galaxy's heartbeat, steady but always there. Here's a creepy thought. We're all orbiting this thing. Earth, the Sun, our entire solar system, we're spiraling around Sagittarius A* in a cosmic dance that takes about 230 million years to complete one lap. We're far enough away to be safe, but it's wild to think we're tied to a black hole's gravity. So what happens when a supermassive black hole isn't so quiet? Let's look at the ones that are wide awake. Not all supermassive black holes are as laid back as Sagittarius A*. Some are absolute terrors, and they're called active galactic nuclei, or AGN. When a black hole has plenty of material to feed on, stars, gas clouds, even other black holes, it turns into a cosmic vacuum cleaner, pulling in matter and heating it to insane temperatures. The result? A blazing disk of superheated gas called an accretion disk, and sometimes powerful jets of particles shooting out at nearly the speed of light. Take quasars, for example. These are the brightest objects in the universe, powered by supermassive black holes in distant galaxies. A single quasar can outshine 1 trillion stars, visible from billions of light-years away. The Atacama Large Millimeter Submillimeter Array, ALMA, has studied quasars like 3C273, which is 2.5 billion light-years away, and found jets stretching hundreds of thousands of light-years. These jets can blast through entire galaxies, shaping star formation and even punching holes in the intergalactic medium. Then there's blazars, a type of AGN where one of those jets is pointed right at us like a cosmic spotlight. The Fermi Gamma Ray Space Telescope has detected blazars emitting gamma rays so energetic they make cosmic rays look tame. And don't forget Seyfert galaxies, which have active black holes but are less extreme than quasars. The Chandra X-Ray Observatory has shown that these galaxies flicker with X-rays as their black holes munch on gas and dust. What's crazy is how these active black holes affect their galaxies. Research from the University of Oxford suggests that their jets and radiation can heat up gas clouds, preventing new stars from forming, or trigger starbursts by compressing gas. It's like they're the galaxy's thermostat, turning star formation on or off. Some scientists even think supermassive black holes and galaxies co-evolve, growing together in a cosmic partnership we're only starting to understand. But here's the chilling part. These active black holes show what happens when a supermassive black hole gets hungry. Could Sagittarius A ever turn into one of these monsters? And what would that mean for us? How do we know so much about these cosmic beasts? It's all thanks to incredible tech like the Event Horizon Telescope and ESA's Gaia mission. The EHT, a planet-wide array of radio dishes, works like a giant virtual telescope, capturing radio waves from the edges of black holes. Its 2022 image of Sagittarius A* was a triumph, but it also imaged the black hole in M87, showing a similar glowing ring around a much bigger monster. According to the Harvard-Smithsonian Center for Astrophysics, these images are helping us test Einstein's theories and understand how black holes warp space-time. Gaia, on the other hand, is like a cosmic GPS, mapping the positions and motions of over 1 billion stars. Its data has been crucial for studying the Milky Way's center, where stars whip around Sagittarius A. By tracking their orbits, Gaia has helped confirm the black hole's mass and size. It's also revealed weird stellar dances, like binary stars getting torn apart by the black hole's gravity, or stars being flung out at incredible speeds, called hypervelocity stars. These missions are giving us unprecedented views of supermassive black holes, but they're also raising new questions. For example, how did these black holes get so massive? Did they grow by eating stars and gas, or did they merge with other black holes? And why is Sagittarius A so quiet when others are raging? The more we learn, the more we realize how little we know. Here's the twist that hits home. We're all orbiting a supermassive black hole, and we hardly ever talk about it. Sagittarius A* might be quiet now, but it's still a force of nature, a point in space where gravity is so intense that nothing, not even light, can escape. Every star in the Milky Way, including our sun, is locked in its gravitational embrace. We're 26,000 light-years away, so we're safe for now. But it's a sobering reminder of how small we are in the cosmic scheme. What's wilder is that supermassive black holes aren't just destroyers, they're creators too. Their gravity helped shape galaxies, pulling gas and stars into the spirals and clusters we see today. Without Sagittarius A*, the Milky Way might not exist as we know it. It's a paradox. We owe our existence to a monster that could, in theory, destroy us. And that brings us to the big question: what happens if Sagittarius A* wakes up? Could it turn into a quasar, blasting radiation across the galaxy? Would it start devouring stars, lighting up the Milky Way's core? Let's explore that chilling possibility. So, we've met the monster at the center. Supermassive black holes ruling galaxies, including our own Sagittarius A*. We've seen how it's quiet now, but other black holes rage, consuming stars and blasting jets that reshape the cosmos. We've marveled at the Event Horizon Telescope's images and Gaia's stellar maps, which pull back the curtain on these beasts. And we've faced the eerie truth that we're orbiting death itself, tied to a black hole's gravity. But here's the question that'll haunt you: what happens when ours wakes up? Scientists at the University of Chicago say it's unlikely to become a quasar anytime soon. There's just not enough gas and dust nearby to fuel a feeding frenzy. But over millions or billions of years, things could change. A passing star could get too close, shredded into a glowing disk. A gas cloud could drift in, sparking a flare of X-rays. Or, in the distant future, when the Milky Way collides with the Andromeda Galaxy, their black holes might merge, creating a new monster that could light up the sky. What would that mean for Earth? At our distance, we'd probably be safe from direct harm, but intense radiation could mess with the galaxy's chemistry, affecting star formation or even cosmic ray levels. Could it disrupt life? Could it trigger changes we can't predict? We don't know, and that uncertainty is what makes supermassive black holes so fascinating and terrifying. The universe is full of these monsters, and we're just starting to understand their power. But what else is out there, shaping the cosmos in ways we can't see? Could there be forces or objects even stranger than black holes, waiting to be discovered? Stick around for the next chapter, because we're diving deeper into the unknown, and it's going to get wild. What happens when ours wakes up? Chapter 6. The coldest places in the universe. Imagine a place so cold that even the idea of warmth feels like a cruel joke. A place where molecules barely wiggle, where the very laws of physics seem to hold their breath. The universe, for all its fiery stars and blazing supernovas, hides corners so frigid they challenge everything we think we know about reality. These are the coldest places in existence, and they're not just chilly, they're mind-bendingly, bone-shatteringly cold. We're talking temperatures like minus 457 degrees Fahrenheit, colder than anything you could ever imagine, colder even than the faint hum of the universe's own background radiation. So, how does a cosmos born in the ultimate explosion, a Big Bang hotter than a trillion suns, end up with places this icy? Let's dive into this frozen mystery. Our first stop is the Boomerang Nebula, a strange glowing cloud of gas and dust about 5,000 light-years away in the constellation Centaurus. This isn't your typical nebula, all warm and sparkly. The Boomerang is the coldest known natural place in the universe, clocking in at a jaw-dropping 1 Kelvin, or roughly minus 457.87 degrees Fahrenheit. To put that in perspective, the average temperature of space, thanks to the cosmic microwave background radiation left over from the Big Bang, is about 2.7 Kelvin, or minus 454.81 degrees Fahrenheit. The Boomerang is colder than the universe's baseline, a place where even the ancient echo of creation feels downright toasty by comparison. Scientists using the Atacama Large Millimeter Submillimeter Array, or ALMA in Chile, along with data from the European Space Agency's Herschel Space Observatory, have peered into this nebula and found something that looks like a cosmic deep freezer. Why is the Boomerang so cold? It's all about what's happening at its heart. At the center of this nebula is a dying star, a red giant that's shedding its outer layers like a snake sloughing off its skin. As it does, it's blasting gas outward at incredible speeds, up to 370,000 miles per hour. This gas expands rapidly, and when gas expands, it cools. Think of it like spraying an aerosol can. The stuff coming out feels cold because it's expanding fast. In the Boomerang, this process is happening on a massive scale, creating a bubble of gas that's chilling down to temperatures we can barely comprehend. But here's the kicker. The nebula's shape, which looks like an hourglass or a bow tie, suggests something's amplifying this cooling effect. Maybe it's the star's magnetic fields, or maybe it's a hidden companion star messing with the gas flow. Scientists aren't entirely sure, and that mystery makes the boomerang even more intriguing. Now, the boomerang isn't the only place in the universe where cold reigns supreme. Let's zoom out to something even stranger. The cosmic voids, those vast, empty stretches between galaxies where almost nothing exists. These voids aren't just empty in the way a deserted parking lot is empty, they're practically devoid of matter, light, and energy. In some of these regions, particle activity drops so low it's almost zero. We're talking about places where the universe feels like it's forgotten how to function. Thermodynamically, these voids are as close to absolute zero, 0 Kelvin, or minus 459.67 degrees Fahrenheit, as you can get in nature. Absolute zero is the point where all molecular motion stops, where entropy, the measure of disorder, hits rock bottom. But here's the thing. Reaching absolute zero is supposed to be impossible, according to the laws of physics. So how do these voids get so close? To understand this, we need to talk about what cold really means. Temperature is a measure of how much particles are jiggling, how much kinetic energy they have. In a hot star, particles are zooming around like cars on a racetrack. In a cold place, they're barely crawling. In cosmic voids, there are so few particles, maybe a single hydrogen atom per cubic meter, that there's hardly anything to jiggle at all. With no stars, no gas clouds, and no radiation to speak of, these voids are the ultimate ghost towns of the cosmos. Data from the Herschel Space Observatory has shown that some of these regions have temperatures so low, they make the Boomerang Nebula look balmy. But what's driving this extreme cold? Is it just the absence of stuff, or is something else at play, some cosmic process we haven't figured out yet? Let's pause for a second and think about what this cold means for the universe. The Boomerang Nebula and these voids aren't just anomalies, they're pushing the boundaries of physics. At temperatures this low, thermodynamics starts acting weird. Quantum effects like Bose-Einstein condensates, where particles start behaving like a single wave, become possible. In labs on Earth, scientists have created these condensates by cooling atoms to just above absolute zero, but in the universe, places like the Boomerang might be natural laboratories for this bizarre behavior. Could these cold spots be hiding clues about the quantum nature of reality, or maybe they're telling us something about the early universe, when everything was squeezed into a hot, dense point before exploding outward? Speaking of the early universe, let's circle back to the Big Bang. About 13.8 billion years ago, the cosmos kicked off with a bang so hot, temperatures in the quintillions of degrees, that it's hard to wrap your head around. As the universe expanded, it cooled, eventually settling into the 2.7 Kelvin background we measure today. But the existence of places like the Boomerang and cosmic voids raises a big question. How do you go from that primordial fire to pockets of such perfect cold? It's like finding a snowflake in a furnace. The universe is supposed to be smoothing out its temperature differences over time thanks to entropy, but these ultra-cold spots seem to defy that trend. Are they relics of some ancient process, or are they being actively cooled by something we don't understand? Speaking of the early universe, let's circle back to the Big Bang. About 13.8 billion years ago, the cosmos kicked off with a bang so hot, temperatures in the quintillions of degrees, that it's hard to wrap your head around. As the universe expanded, it cooled, eventually settling into the 2.7 Kelvin background we measure today. But the existence of places like the Boomerang and cosmic voids raises a big question. How do you go from that primordial fire to pockets of such perfect cold? It's like finding a snowflake in a furnace. The universe is supposed to be smoothing out its temperature differences over time thanks to entropy, but these ultra-cold spots seem to defy that trend. Are they relics of some ancient process? Or are they being actively cooled by something we don't understand? Let's dig a bit deeper into the Boomerang Nebula, because it's a real head-scratcher. When astronomers first spotted it with the Hubble Space Telescope, they thought it looked like a bow tie, hence the name. But ALMA's sharper images revealed a more complex structure, with lobes of gas stretching out like the wings of a butterfly. This shape suggests the star at the center isn't just puffing out gas randomly, it's being sculpted by something. Maybe it's a binary star system, where two stars orbit each other, stirring up the gas like cream in coffee. Or maybe it's a single star with a weird magnetic field. Either way, the rapid expansion of this gas is key to the nebula's record-breaking cold. But why is it so much colder than other nebulae? Other dying stars shed gas too, but none come close to the boomerang's icy grip. One theory is that the boomerang star is losing mass at an insane rate, about 100 times faster than similar stars. This mass loss creates a kind of cosmic wind that accelerates the cooling process. But even that doesn't fully explain the temperature drop. Some scientists think the nebula's unique shape traps cold gas in a way that amplifies the effect, like a refrigerator with perfect insulation. Others wonder if there's something exotic going on, like dark matter or some unknown particle sapping energy from the system. The truth is, we don't know, and that's what makes the boomerang so fascinating. It's a reminder that even in a universe we've studied for centuries, there are still places that defy our best theories. Now let's swing back to those cosmic voids. These aren't just empty spaces, they're the scaffolding of the universe. Galaxies and galaxy clusters form a web-like structure, with voids as the gaps between the threads. Some voids are hundreds of millions of light-years across, so vast that light from one side would take longer to reach the other than the universe has been around. In these regions there's so little matter that gravity barely has anything to work with. Without stars or gas to generate heat, these voids are naturally cold, but their near-zero particle activity pushes them into uncharted territory. According to ESA's Herschel data, some voids have effective temperatures so low they're practically indistinguishable from absolute zero. But what does that mean for the laws of physics? At these temperatures, the universe starts flirting with the impossible. The third law of thermodynamics says you can't reach absolute zero because it would require infinite energy to remove all heat from a system. Yet these voids seem to get awfully close. Are they bending the rules, or are we misunderstanding something fundamental about temperature and entropy? Some physicists think these voids could be testing grounds for theories about dark energy, the mysterious force driving the universe's expansion. Since dark energy seems to dominate in empty spaces, maybe it's influencing the temperature of these voids in ways we haven't figured out. Or maybe the voids are so empty they're essentially outside the normal flow of cosmic evolution, frozen in time like a snapshot of the early universe. Let's take a step back and think about why these cold places matter. The universe is a story of contrasts, hot and cold, light and dark, chaos and order. The existence of places like the Boomerang Nebula and cosmic voids tells us that the cosmos isn't just a homogeneous soup of stars and gas, it's a place of extremes, where the rules we take for granted can bend or even break. These cold spots challenge our understanding of how the universe evolved from a hot, dense beginning to the sprawling, complex web we see today. They also raise big questions about what normal means in a cosmos that's anything but. For example, consider the implications for life. We think of life as needing warmth, like the cozy Goldilocks zone around stars where water stays liquid, but what if the coldest places in the universe are hiding something we haven't considered? Maybe not life as we know it, but some kind of exotic process that thrives in the deep freeze. Or maybe these cold spots are clues to the universe's ultimate fate. As the cosmos expands, it's getting colder overall. Billions of years from now, will the whole universe look like a giant cosmic void with stars burned out and temperatures inching toward absolute zero? If so, what does that say about the legacy of everything we see today? Let's zoom in on the science for a moment. The Boomerang Nebula's temperature was measured using ALMA's ability to detect sub-millimeter wavelengths, which let astronomers map the nebula's gas and dust in exquisite detail. The data showed that the nebula's outer regions are absorbing the cosmic microwave background, effectively using the universe's own radiation as a backdrop to cool even further. This is wild when you think about it. A place in the universe is so cold it's stealing heat from the Big Bang's afterglow. Meanwhile, Herschel's infrared observations of cosmic voids revealed their eerie stillness. With so little thermal activity, they're like blank spots on the cosmic map. These discoveries weren't easy. They required cutting-edge telescopes and years of analysis to confirm. But they've given us a glimpse into a side of the universe we rarely think about. Now let's get philosophical for a second. The coldest places in the universe aren't just scientific curiosities, they're a reminder of how little we know. The Boomerang Nebula, with its impossible chill, feels like a puzzle piece that doesn't fit. Cosmic voids, with their near absolute zero stillness, seem to mock our attempts to understand the cosmos. Together they suggest that the universe is full of surprises, places where our best theories falter. What's causing these extreme conditions? Are they accidents of cosmic evolution, or are they pointing to something deeper, some fundamental truth we haven't grasped? As we wrap up this chapter, let's linger on the strangeness of it all. The universe began in unimaginable heat, a fireball that birthed everything we know. Yet somehow it sculpted these pockets of perfect cold, places where the chaos of creation has given way to an eerie calm. The Boomerang Nebula glows faintly, a dying star's last gasp frozen in time. Cosmic voids stretch across unimaginable distances, silent and still, like the universe holding its breath. These places aren't just cold, they're a challenge to our understanding, a whisper that there's more to the cosmos than we've dreamed. So, here's the question that lingers. Why is there such perfect cold in a universe born in fire? Is it just physics doing its thing? Or is there a deeper reason, some cosmic purpose we can't yet see? The answer might be out there, waiting in the icy shadows of the universe, ready to change everything we think we know. Picture this, you're standing in a vast dark forest, but instead of trees, there are galaxies, billions of them, strung together like glowing beads on an endless, intricate spiderweb. This isn't some fantasy, it's the universe we live in, and scientists call this sprawling network the cosmic web. It's a structure so massive, so complex, it defies imagination. But here's the kicker. When you zoom in on this web, it starts to look eerily familiar, like the neural network inside your brain. Could this cosmic structure be more than just a collection of stars and galaxies? Could it be alive, thinking, maybe even conscious? Let's dive into this mystery. Guided by the groundbreaking work of the Sloan Digital Sky Survey and simulations by astrophysicist Miguel Aragon, and see if we can unravel what this cosmic web really is, and what it might mean for us. The universe isn't a random scatter of stars and planets. It's organized, structured, like a city with highways and neighborhoods. The cosmic web is the framework that holds it all together. Imagine filaments, long, glowing threads of galaxies, stretching across billions of light years. These filaments connect at massive hubs called galaxy clusters, where hundreds or thousands of galaxies huddle together. Between them lie vast, empty regions called voids, and thin, sheet-like walls that separate these voids. It's a pattern that repeats across the observable universe, a network so large it takes light billions of years to cross it. The Sloan Digital Sky Survey, or SDSS, has been our window into this structure. Since the early 2000s, this massive project has mapped over 1 million galaxies, creating a 3D picture of the universe's architecture. Using telescopes at Apache Point Observatory in New Mexico, SDSS measures the light from galaxies to figure out their distances and positions. What it's revealed is stunning. Galaxies don't just float aimlessly. They're woven into this intricate web, with filaments that can stretch up to 1.37 billion light-years, like the Sloan Great Wall discovered in 2003. This isn't just a pretty picture, it's a map of the universe's skeleton, formed by gravity over billions of years. But how did this web come to be? It started with the Big Bang, 13.8 billion years ago. Back then, the universe was a hot, dense soup of particles. Tiny fluctuations in density, think of them as ripples in a pond, began to grow under gravity's pull. Over time, these ripples became the seeds of galaxies, clusters, and filaments. Astrophysicist Miguel Aragon has used powerful computer simulations to recreate this process. His work shows how matter clumps together, forming dense nodes and long, thread-like structures, while leaving vast voids behind. These simulations match what SDSS observes, confirming that the cosmic web is real, not just a trick of the telescope. But why does this structure look so deliberate, and what does it mean that it resembles something we know so well? A neural network in the sky? Here's where things get weird. In 2020, astrophysicist Franco Vazza and neurosurgeon Alberto Folletti published a study that sent ripples through the scientific community. They compared the cosmic web to the human brain's neural network, and found uncanny similarities. The human brain has about 69 billion neurons, connected by synapses, in a complex web. The observable universe? It's got roughly 100 billion galaxies, linked by those filaments we mentioned. When you look at a slice of the brain under a microscope, you see neurons and their connections forming a web-like pattern. Zoom out to the cosmic web, and you see galaxies and filaments in a strikingly similar arrangement. Vazza and Folletti didn't stop at visuals. They crunched the numbers, analyzing the density fluctuations in both systems. In the brain, neurons cluster in certain areas, with gaps in between. In the universe, galaxies cluster along filaments, with voids separating them. The researchers used a technique called spectral density analysis, often used in cosmology to study galaxy distributions. They found that the way matter fluctuates in the cosmic web, on scales from 5 million to 500 million light-years, follows a pattern remarkably similar to how neurons fluctuate in the brain on scales from 1 micrometer to 0.1 millimeters. The numbers line up. Both systems have about 25 to 30% of their mass in the active components, neurons or galaxies, while the rest is passive material, like water in the brain or dark energy in the universe. But it's not just about looks or density. The connections matter too. In the brain, each neuron might connect to 5 others on average, forming a network that processes information. In the cosmic web, galaxy clusters connect to about 4 filaments on average, creating a network that channels matter and energy. Vatsa and Folletti's study suggests that both systems might be shaped by similar principles of network dynamics, even though they operate on scales billions of times apart. It's like nature is using the same blueprint for 2 wildly different systems. But why? Is this just a coincidence? Or is there something deeper at play? Miguel Aragon's simulations, building the web. To understand the cosmic web better, let's turn to Miguel Aragon's work. As an astrophysicist, Aragon has spent years creating simulations that model how the universe evolves. These aren't simple animations. They're complex calculations run on supercomputers based on the laws of physics. Aragon's simulations start with the early universe, a chaotic mix of matter and energy. They factor in gravity, dark matter, and dark energy, then let the universe run for billions of years. The result? A digital cosmic web that mirrors what SDSS observes. Filaments, clusters, walls, and voids, all emerging naturally from those initial conditions. Aragon's work, often built on data from surveys like SDSS, shows that the cosmic web isn't static, it's dynamic, evolving as gravity pulls matter into denser regions. His simulations reveal how filaments form, dark matter, an invisible substance that makes up about 27% of the universe's mass, acts like scaffolding. Galaxies form where dark matter is densest, and over time, they align along these filaments like pearls on a string. Voids, meanwhile, are regions where matter has been pulled away, leaving vast empty spaces. Aragon's models also show how the web's structure depends on scale. On smaller scales, say a few million light-years, filaments are sharp and distinct. On larger scales, the universe starts to look more uniform, almost like a sponge. What's fascinating is how these simulations align with real observations. The SDSS data, for instance, shows filaments extending up to 30 megaparsecs, about 98 million light-years, before they blend into a more homogeneous network. Aragon's simulations confirm this, suggesting that the cosmic web has a characteristic scale where its patterns are most pronounced. But here's the question that lingers. If the universe is so structured, so organized, could it be more than just a physical system? Could it have properties we associate with life or even intelligence? Is the universe alive? Now, let's push the boundaries a bit. The similarity between the cosmic web and the brain's neural network has sparked some wild ideas. Could the universe be a giant brain, capable of thought or consciousness? It sounds like science fiction, but hear me out. It's a question scientists are starting to take seriously. The cosmic web structure, with its nodes and connections, resembles a network that could, in theory, process information. In the brain, neurons fire signals to communicate, creating thoughts and memories. In the universe, galaxies and clusters exchange matter and energy along filaments. Could this exchange be a form of cosmic thinking? Let's look at the numbers again. The human brain's memory capacity is estimated at about 2.5 petabytes. That's 2.5 million gigabytes. Vaza's work suggests the cosmic web's complexity, based on simulations, requires 10 petabytes to describe. That's in the same ballpark, but there's a catch. The universe operates on a much slower timescale. Signals in the brain travel in milliseconds. In the universe, a signal traveling at the speed of light would take millions, even billions of years to cross from one galaxy cluster to another. If the universe is thinking, it's doing so at a glacial pace, maybe 1,000 exchanges since the Big Bang, compared to billions in your brain every day. Still, the idea persists. Some researchers, like physicist Roger Penrose, have speculated that consciousness might arise from quantum processes in the brain. Could similar processes happen on a cosmic scale? The universe is full of quantum effects, after all, from the early fluctuations that seeded the cosmic web to the behavior of particles in black holes. Others, like philosopher Philip Goff, argue for panpsychism, the idea that consciousness might be a fundamental property of matter present even in the simplest particles. If that's true, the cosmic web, with its vast network of connections, could be a kind of cosmic consciousness, a mind on a scale we can't comprehend. But let's not get too carried away. There's a big difference between structural similarity and functional similarity. Just because the cosmic web looks like a brain doesn't mean it acts like one. The brain's connections are dynamic, constantly rewiring based on experience. The cosmic web, while evolving, is shaped by gravity and dark energy, not by anything we'd call learning. Plus, the universe is expanding, pulling galaxy clusters apart faster than ever. If it's a brain, it's one that's slowly unraveling. So, is the universe alive? Intelligent? We don't know, but the question is tantalizing. If this feels like science fiction, it's not. This is real science, backed by data from the Sloan Digital Sky Survey and simulations by researchers like Miguel Aragon. The universe is stranger, more connected, and more mysterious than we ever imagined. Want to dive deeper into these cosmic enigmas? Subscribe for more documentaries like this where we explore the biggest questions about our place in the universe. We've mapped the cosmic web, compared it to the human brain, and even wondered if it could be conscious. But here's the question that keeps me up at night. What if the universe isn't just a place we live in, but a being we're part of? If the cosmic web is a kind of mind, what is it thinking about, and are we, tiny specks within it, somehow part of its thoughts? The answers might be out there, hidden in the filaments and voids, waiting for us to find them. Chapter 8. Time is an Illusion. Hey, cosmic explorers, welcome back to Mysteries of the Universe. We've journeyed through the invisible forces shaping our solar system, the ghostly Oort cloud flinging comets our way, and the dark matter and energy that dominate the cosmos. But today, we're tackling something even weirder, something you experience every day, but might not actually understand. We're talking about time. Is it a straight line from past to future? Does it flow like a river? Or is it something so strange that everything we think we know about it is wrong? Thanks to Einstein's theory of relativity, experiments like NASA's Gravity Probe B, and wild ideas from physicists at places like Princeton, we're diving into a universe where time slows down near gravity, almost stops near black holes, and might not even exist the way we think. Buckle up, because this one's gonna mess with your head, and leave you wondering if time is just an illusion we're all trapped in. Time and gravity, Einstein's cosmic curveball. Let's start with a guy who changed everything, Albert Einstein. Back in 1915, he dropped a bombshell called general relativity, and it's still one of the most mind-bending ideas in science. According to Einstein, time isn't the same everywhere, it's stretchy, like a rubber band. The stronger the gravitational pull in a place, the slower time moves. It's not just a theory, it's been tested and proven over and over again. Picture this, you're standing on Earth, checking your watch. It's ticking along just fine. But if you hopped on a spaceship and flew close to a massive object like a black hole, time would start to crawl. If you parked right near the event horizon, the point of no return around a black hole, seconds for you could be years for someone back on Earth. This isn't sci-fi, it's real. NASA's Gravity Probe B, launched in 2004, tested this idea by measuring how Earth's gravity warps space-time. The results, published in Physical Review Letters, confirmed Einstein was right. Clocks tick slightly slower on Earth's surface compared to ones in orbit, where gravity is weaker. Why does gravity mess with time? It's because space-time, the fabric of the universe, isn't flat. Massive objects like planets, stars, or black holes bend it, like a bowling ball sitting on a trampoline. Time gets stretched in those dents, slowing down for anyone caught in them. Researchers at Princeton have used super-precise atomic clocks to measure this effect, showing that even moving a clock a few feet higher off the ground, where gravity is slightly weaker, makes it tick just a tiny bit faster. This is wild when you think about it. If you lived on a planet with stronger gravity than Earth, you'd age slower than your friends on a less massive world. It's called gravitational time dilation, and it's not just a quirk, it's a fundamental truth about the universe. But what happens when you take this to the extreme, like near a black hole? That's where things get really bizarre. Black holes, where time almost stops. Let's zoom out to the most extreme objects in the universe, black holes. These are places where gravity is so intense that not even light can escape. And when it comes to time, black holes are like the ultimate time machines, or time freezers. The closer you get to a black hole's event horizon, the slower time moves until, right at the edge, it almost stops. Imagine you're an astronaut floating near a black hole, while your buddy stays safe on a spaceship far away. From your buddy's perspective, as you drift closer to the event horizon, your movements slow down. Your radio signals take longer to reach them. Eventually, you'd appear to freeze, hovering just outside the black hole forever. But from your perspective, You'd keep falling, maybe even crossing the event horizon without noticing anything weird. This is called the no-hair theorem in black hole physics, studied by folks like John Wheeler at Princeton. It says black holes don't care about your personal experience of time, they warp it for everyone else. This effect was beautifully shown in the movie Interstellar, where time dilation near a black hole meant hours on a planet equaled years back on Earth. But it's not just Hollywood drama. NASA's studies of black holes using telescopes like Chandra and Newton show that matter spiraling into a black hole experiences extreme time dilation. X-rays emitted from material near the event horizon arrive at our telescopes stretched out, a sign that time itself is being warped. Here's the crazy part. What happens if you fall into a black hole? Does time stop completely? Scientists aren't sure because we can't see past the event horizon. Some theories, like those from physicist Kip Thorne, suggest you'd hit a singularity, a point of infinite density where the laws of physics, including time, break down. Others, like string theory ideas from researchers at Stanford, hint that time might loop or transform in ways we can't imagine. The truth, we're still guessing because no one's come back from a black hole to tell us. This leads to a bigger question. If time can bend and stretch like this, is it even real? Or is it just a trick our brains play to make sense of the universe? That's where some mind-blowing theories come in, suggesting time might not work the way we think at all. Now let's get really wild. What if time isn't a river flowing from past to future? What if it's more like a giant frozen block where everything, past, present, future, exists all at once? This is called the block universe theory, and it's one of the most head-spinning ideas in physics, backed by some heavy hitters at places like Princeton and Caltech. The block universe comes from Einstein's relativity, too. If time can stretch and bend depending on where you are, then maybe our idea of now is just a slice of a bigger reality. Imagine the universe as a four-dimensional block, with 3 dimensions of space and 1 of time. Every moment, your birth, this second right now, the end of the universe, is already there, like frames in a movie reel. You're just moving through it, experiencing one slice at a time. Philosophers and physicists like Hermann Minkowski, who helped develop this idea, say it's not just a metaphor, it's how space-time actually works. Here's where it gets freaky. If the block universe is real, then the past, present, and future are equally real. That time you tripped in front of your crush in high school? It's still happening in some sense, in its own slice of the block. The year 3000? It's already out there, waiting. Studies from Princeton's Institute for Advanced Study, like those by physicist David Deutsch, argue that quantum mechanics supports this idea. In quantum theory, particles can exist in multiple states at once, so why not time? This raises some wild possibilities. If every moment exists forever, are there other versions of you out there living different choices? Maybe in one slice of the block you're an astronaut orbiting a black hole, while in another, you're eating pizza on your couch. This ties into the many worlds interpretation of quantum mechanics, where every decision splits the universe into parallel timelines. So maybe you're already dead in one version of this timeline, and alive, thriving, or even immortal in another. But here's the catch. We don't feel like we're in a block universe. We feel time moving forward, 1 second at a time. Why? Some physicists, like Sean Carroll at Caltech, say it's because of entropy, the universe's tendency to move from order to disorder. It's like an arrow pointing one way, giving us the illusion of time's flow. Others, like those at the Perimeter Institute, argue our brains are just wired to perceive time linearly, even if it's not. Let's pause for a second and let that sink in. If the block universe is real, every version of you, past, present, future, or even in alternate timelines, exists right now. That moment you're most embarrassed about, it's frozen in the block, happening forever. That dream you haven't chased yet? It might already be real in another slice, and yeah, there might be a timeline where you didn't make it past last Tuesday, but here you are, watching this video in another. This isn't just philosophy, it's backed by hard science. NASA's Gravity Probe B confirmed that space-time warps exactly as Einstein predicted, supporting the idea that time is just another dimension, like height or width. Quantum experiments, like those at the University of Vienna, show particles behaving as if they know the future, hinting that time might not be as straightforward as we think. And black hole studies, using data from ESA's Newton, keep showing us that time can twist in ways our brains struggle to grasp. But here's what keeps scientists up at night. If time is an illusion, why do we experience it so vividly? Is it just our brains tricking us? Or is there something deeper, maybe a hidden structure to the universe, that makes time feel real? We're only starting to scratch the surface, and every answer leads to more questions. So, we've seen how gravity warps time, how black holes nearly stop it, and how the block universe suggests every moment exists at once. We've got experiments proving time dilation, theories suggesting parallel timelines, and a universe that might not care about our clocks at all. But here's the question that'll stick with you. What if time doesn't move? And only we do. Think about it. If the block universe is real, time isn't flowing, it's just there. Like a road. We're the ones moving through it, experiencing each moment like pages in a book. But what if we could step outside that book? What if we could see the whole story? Past, present, future, all at once. Would we still be human, or would we become something else, something that understands the universe in a way we can't even imagine? We're not done yet. The universe has more mysteries to throw at us, from parallel worlds to the edges of reality itself. What's out there, beyond our perception of time? Could there be a place where time doesn't exist at all? Stick around for the next chapter, because we're diving deeper into the unknown, and trust me, it's gonna get even weirder. What if time didn't move, and only we do? Imagine waking up one day and realizing everything around you, your coffee mug, the morning sun, even the thoughts running through your head, might not be real. Not in the way you think, at least. What if the world, the stars, the entire universe is just a super sophisticated computer program? A simulation like a video game, but so advanced you can't tell the difference. Sounds like something out of a sci-fi movie, right? But here's the wild part. Some of the smartest people on Earth, scientists, philosophers, even tech billionaires, are seriously asking, are we living in a simulation? Welcome to the simulation hypothesis, a mind-bending idea that makes you question the very nature of reality. Let's start with a simple question. What is reality? You might say it's the stuff you can see, touch, and feel. The chair you're sitting on, the phone in your hand, the stars in the night sky. But what if all of that is just code? Think about a video game like The Sims. The characters in the game go about their lives, work jobs, fall in love, and never suspect they're just bits of data being controlled by someone outside their world. Now, what if we're the Sims? What if everything we know, our planet, our galaxy, even our emotions, is part of a massive computer program designed by someone or something we can't even imagine? This idea didn't just come out of nowhere. It's rooted in some serious thinking by people who spend their days studying the universe. One of the biggest names behind this is Nick Bostrom, a philosopher at Oxford's Future of Humanity Institute. Back in 2003, Bostrom wrote a paper that shook up the academic world. He argued that at least one of these three things must be true. 1. Advanced civilizations never reach the point where they can create super-realistic simulations. 2. Advanced civilizations that can create simulations choose not to for some reason. Or 3. We're almost certainly living in a simulation right now. Let's break that down. First, let's talk about the tech. Computers today are already insanely powerful. Think about how far we've come in just a few decades. In the 1980s, video games were blocky, pixelated things like Pac-Man. Now we have games with graphics so real you can almost feel the wind in a virtual forest. Our computers double in power roughly every 2 years, something called Moore's Law. If that keeps up, imagine what computers could do in 100 years or 1,000. A civilization way more advanced than ours could build a computer capable of simulating an entire universe down to every blade of grass, every raindrop, every thought in your head. And here's the kicker. If they can simulate one universe, they could simulate billions. So, statistically, it's more likely we're in one of those simulated universes than the one real one. But it's not just about computing power. The universe itself seems to act like it's built on code. Scientists have noticed something weird. The laws of physics, the rules that govern how everything works, look a lot like digital logic. Take quantum mechanics, for example. At the tiniest scales, particles don't exist in one place or another. They exist in a kind of fuzzy probability until you observe them. It's almost like the universe only renders reality when it needs to. Like a video game saving processing power by only loading the part of the map you're looking at. Then there's something called the Planck length, the smallest possible distance in the universe. About a billionth of a billionth of a billionth of a meter. Nothing smaller than that seems to exist. It's like the universe has a resolution limit, the way a computer screen has pixels. These clues make some scientists wonder, is the universe digital at its core? Even NASA has gotten in on this. Some researchers there have run experiments to look for glitches in reality, patterns or behaviors in the universe that don't add up, like bugs in a computer program. They've studied things like cosmic rays, the high-energy particles zipping through space, to see if they act in ways that suggest a digital structure. So far they haven't found anything conclusive, but the fact that they're even looking shows how seriously this idea is taken. It's not just a thought experiment anymore, it's something scientists are actively testing. Now, let's talk about someone you've probably heard of. Elon Musk. Yeah, the guy who builds rockets and electric cars. He's one of the biggest cheerleaders for the simulation hypothesis. Musk has said publicly that he thinks there's a 1 in billions chance we're not living in a simulation. His reasoning? If advanced civilizations can create simulations and they make a ton of them, then the odds of us being in the base reality, the original non-simulated universe, are tiny. It's like picking one specific grain of sand on a beach. Musk's not alone either. Other tech minds like Neil deGrasse Tyson and even some Silicon Valley coders have jumped on this idea, saying it makes sense when you look at how fast our own tech is evolving. So let's say for a second that we are in a simulation. Who's running it, and why? That's where things get really wild. Maybe it's an advanced civilization studying their past, like a cosmic history project. Maybe they're running simulations to figure out how to avoid some disaster that wiped them out. Or maybe it's just for fun, like someone playing The Sims on a galactic scale. Imagine a kid in a super advanced world hitting start on their universe simulator and poof, here we are living our lives, unaware we're part of their game. But here's another possibility. What if the simulation isn't perfect? Every computer program has bugs, right? Those weird, unexplainable things in our world, the mysteries we've been talking about in this documentary, could they be glitches in the system? Think about it. Black holes, dark matter, the Fermi Paradox we talked about earlier, what if these aren't just puzzles waiting to be solved? What if they're errors in the code? Maybe the reason we can't find aliens is because the simulation only programmed one intelligent species, us. Or maybe the laws of physics break down at certain points because the programmers didn't account for every scenario. It's a chilling thought. The greatest mysteries of the universe might just be sloppy coding. Let's take it a step further. If we're in a simulation, could we ever figure it out? Some scientists think we might be able to spot clues. For example, if the universe has a resolution limit like a computer screen, we might notice it in experiments at super tiny scales. Others say we could look for patterns in nature that seem too perfect, like something designed rather than random. But here's the problem. If the simulation is good enough, we might never know. The programmers could be so advanced that they've hidden all the evidence. Or worse, what if they're watching us right now, tweaking the code to keep us from finding out? This idea can mess with your head. If we're in a simulation, are our choices even real? Do we have free will, or are we just following a script? And what about the big questions we ask? About life, love, the meaning of it all? Are those just part of the program designed to keep us busy? It's enough to make you want to unplug from the whole thing. But here's the crazy part. Even if we're in a simulation, it doesn't make your life any less real to you. Your joys, your struggles, your dreams, they feel real, and that's what matters. Or does it? There's one last twist to consider. If we're in a simulation, who's behind it? Are they like us, just more advanced? Or are they something totally alien, something we can't even imagine? And why would they create us, to study us, to entertain themselves? Or maybe, here's the spooky part, maybe we're not the main characters. Maybe we're just background noise in someone else's story, like NPCs in a video game. The universe is so vast, so full of mysteries, that it's hard not to wonder, what if the real action is happening somewhere else and we're just a tiny piece of the code? The simulation hypothesis doesn't give us answers, it just gives us more questions. And maybe that's the point. Maybe the universe is designed to keep us curious, to keep us searching. But as you sit there staring at the stars or scrolling through your phone, think about this. What if the truth isn't out there in the cosmos? What if it's buried deep in the code of reality itself? If we're living in a simulation, who pressed start? We've traveled far in this journey, from the edges of black holes to the possibility that our entire reality is just a line of code. The universe is a wild, mysterious place, full of questions that make your brain hurt and your heart race. But here's the thing. Maybe we're not supposed to solve it all. Maybe the whole point of these mysteries, the Fermi Paradox, dark matter, the simulation we might be living in, is to keep us wondering, to keep us reaching for something bigger. The universe doesn't owe us answers. It doesn't hand us a guidebook or a cheat code. Instead, it gives us questions, big ones, that push us to think deeper, to dream wilder, to explore further, And that's where the real adventure begins, not out there in the stars, but right here, in your mind, in the way you see the world. So what's next? Keep asking questions, keep looking up, subscribe for more deep dives into the unknown because we're just getting started. The mysteries of the universe won't end, but your journey through them can begin now. And who knows, maybe the real frontier isn't out there in the cosmos, maybe it's inside you, waiting to be explored.